All right, so I'd like to, in this video, go over the questions and problems that you worked on in class, and then cover a couple additional topics for this unit, which would be angular momentum and conservation of angular momentum. So let's look at the questions and problems that you were tackling at the end of class yesterday. All right, so here we have a bowling ball rolling down a ramp and is asking which forces exert a torque on the bowling ball about its center. So they do list a couple different forces, and I think it's helpful to label them. We have the weight, which is going to act straight down. We have the normal force, and then we have the friction. Keeping in mind that torque, I'm just going to look at the magnitude of it, is RF sine of theta. Remember that R, that radius vector, goes from the point of rotation to where the force acts. Of course, for the bowling ball, the point of rotation is through the center, and because that's the way it rotates about its center. So when you look at normal and the weight, they both actually they act through the center, or the forces pass through the center. So for both of those, the radius vector would have a length of 0, which means those two forces will not produce a torque that would cause the ball to roll. But you can see that for the frictional force, the radius vector, if we just draw it in red, and just did a big R, would actually be the radius of the bowling ball. And so it turns out that the correct answer to this is the frictional force exerted by the ramp. The weight and the normal force do not, because they act through the center. All right, so here we're asked to look at the translational kinetic energy of a sphere as it's rolling without slipping. So the translational kinetic energy is 1/2 mvcm squared. The rotational kinetic energy is 1/2 I omega squared. Pieces of information that we're going to use is the moment of inertia of the sphere is 2/5 mr squared, and because it's rolling without slipping, the relationship between the velocity of the center of mass and the angular velocity is given with this expression. What I want to do is I need to express both of these quantities in the same variables. What that's going to entail is substituting the value in for moment of inertia, and then we make a choice. Are we going to write kinetic energy in terms of the omega or the v? And so different students made different choices, but you will get the right answer regardless. So I chose to just keep things in terms of the velocity of the center of mass. So this is the translational kinetic energy. I'm going to rewrite the rotational kinetic energy. The first thing I'm going to do is substitute in the expression for the moment of inertia of a solid sphere. And then I'm going to substitute in for omega, the velocity of the center of mass divided by the radius, and that has to be squared. So a couple of things will simplify. The 2's cancel out, the r squares cancel out, and I find that the rotational kinetic energy ends up to be 1/5 mvc sub m squared. And so now really I can just compare the fractions out front, because now they're written in terms of the same variables. And obviously 1/2 is bigger than 1/5, so the translational kinetic energy is larger. I had an extra slide for working. All right, and so here we have a sphere and a hoop are placed at the top of an inclined plane with an angle of 30 degrees. So let's just draw it. Here's 30 degrees. We want to find the speed at the bottom of the inclined plane, so we're going to start at the beginning, we're going to end at the bottom, and the distance along the plane, so that's the hypotenuse, is 3 meters. They give you the 2 moments of inertia and also information about the mass of the sphere and the radius, and also the mass of the hoop and its radius. Now, what I found when I was looking around is some people were doing this. This was a result I got in class. But you can't use that. I think I made it clear, but I want to make it clear again. I did it to sort of talk about what happens and, the idea that the radius didn't matter, the mass didn't matter. But it doesn't mean that we can just routinely use this equation to find the result of the speed at the bottom of the incline using conservation of energy. I want you to be able to do it. So I do want you to use conservation of energy by looking at the kinetic and potential energy, both at the top and the bottom of the incline. I've already marked my initial point and my final point. So let's do the sphere first. It starts from rest, so its initial kinetic energy is 0. We're just going to write the mass of the sphere, GH. I'm going to substitute in for H in the next step. At the bottom, it has translational kinetic energy, and it will also have rotational kinetic energy, and it doesn't have any potential energy. This is H. You can see that H could be written as 3 times the sine of 30. So I'm going to substitute that in down here and do some other substitutions. I just happened to bring the square in there already. So what I did in this step, I wrote the expression for the height, and then I substituted in for the moment of inertia of a solid sphere. And then I also substituted in for omega, the velocity over the radius, and that whole thing is squared, which I already did. So I wanted to just kind of make that clear, what I did in this step. Notice all the masses cancel out, the radius cancels out, and let's just write what I have left. All right, so what's 1/2 and 1/5? Common denominator of 10, this is 5 and 2. And so that's 7/10. So if we solve for the velocity, which is going to be at the top, at the bottom, sorry. Sine at 30. And I got 6.52, well, it's 5.3, sorry, meters per second. And the thing that I hope you noticed is the mass and the radius cancel. So the speed does not depend on those two quantities. And we can go to the page to have room to do the hoop. Everything is going to be pretty much the same, but we're going to have a different moment of inertia. We know what h is, so I'm just going to substitute it in a little earlier. No initial kinetic energy, no final potential energy. I'm going to substitute in for the moment of inertia and omega. And again, mass cancels, the r squares cancel. I get g times 3 sine 30 equals 1/2 VCM squared. Here we just have 1/2 VCM squared. So I can add a half and a half. That one's easy. And I get 3.83 meters per second. This is a lot slower, which we expected because it had a higher moment of inertia. And once again, the mass and the radius cancel, so it does not depend on the mass or the radius of the object. It doesn't actually matter. It only matters that there was a sphere and a hoop. All right, so here we have a glider on a frictionless horizontal track. It's connected to an object of mass 2 on a massless spring. The glider accelerates to the right, so here's our acceleration. This means also that the angular acceleration of the pulley is going to be in that sense. They want us to figure out what the relationship is among T1 and the tension T2. So for one, if we have T2 is going to be less than M2G because it accelerates down, so that has to be true. And if we look at the tensions as they apply to the pulley, because the pulley rotates clockwise, we also see that T2 has to be greater than T1 because it's going to provide the dominant torque to make the clockwise rotation. So if we put that all together, T1 is the smallest. It's smaller than T2, which is smaller than M2G. And so that would correspond to C. Okay, so here is a problem where we're looking at the relationship of torque to moment of inertia and angular acceleration. We're talking about a flywheel, which is an object that spins. It can be more like a wheel with spokes, or it could be a disc. It doesn't really matter because they tell us the total value of the moment of inertia. We're told that omega naught is 0 and omega final is 200 radians per second, and the amount of time that it changes is 5 seconds. So the first thing they're asked is to find the angular acceleration, which will be 200 divided by 5, which is going to be 40 radians per second squared. And then to find the torque, it's just a substitution of the moment of inertia and our alpha that we just found. So we have 50 times 40, which is 20, 2 more zeros, and that's going to be measured in Newton meters. And that's the magnitude of the torque. So here's a problem that's going to ask us to look at the relationship of torque equals I alpha, but we're also going to combine our information about forces is MA. And we're going to label the forces on the two masses and then on the pulley, and then kind of combine everything. So for A, we have normal, we have MAG, and I'm going to call this T1. I think everything's going to move this way, down, and so this is going to be the alpha of the pulley. For the block B, I have T2, M2G. So the first thing I'm going to look at block A and block B and look at their forces. For mass, I am only going to worry about forces in the x direction. In the y direction, I have normal and the weight, but I would only use those values if I had friction, and I don't, because we're told it's a frictionless surface. So finding the fact that the normal and the weight are equal is nice, but I'm not going to use it. So the only force that I have is T1. It's in the same direction as the acceleration. So I have T1 is equal to M1A. If I look at mass B, that's accelerating downward. We're going to say forces in the y. I have T2 minus M2G. Because it accelerates down, I have minus M2A. And so I got that. So I have these two expressions, and now I have to look at the pulley. So for the pulley, I need to redraw my tensions because I want to see how they act on the pulley itself. They're going to cause a torque. That's going to give the angular acceleration. It's going to go counterclockwise, so I'm going to write T2 first. The torque is T2 times the radius of the pulley. The T1 is in the opposite direction. We're just given the moment of inertia, and there's alpha. I want to find an expression for acceleration, so I'm going to use the fact that the angular acceleration is the normal acceleration over the radius. And so I have T2 R naught minus T1 R naught is equal to I A over R naught. I'm going to divide both sides by R naught again. And now I'm going to use these two expressions to substitute in for T2 and T1. For T2, I have M2G minus M2A. For T1, I have just minus, sorry, this is, it should be, I wrote 2. All right. So I only have MBG is equal to IA over R squared plus MBA plus MAA. I'm going to go over here, kind of try to organize this a little nicer. I want to find A, so I'm going to factor it out of the right-hand side. And then I can divide by the quantity that's in the parentheses. And that's my expression for acceleration. All right, so the next thing is we're going to introduce a new quantity. Similarly to how we had regular momentum in Chapter 9, we are going to introduce sort of a rotational equivalent to momentum, and we will call it angular momentum. Now, the difference is that angular momentum still really deals with the motion of an object, but because it allows for rotation, we are measuring it relative to a point, and there is a radius vector from that point to where our mass is. And what we're doing is the angular momentum, which are going to use the little letter L, is going to be defined as the cross product of the radius vector and the momentum vector. So we can write it as R cross mv. And that would be for the case when there is a point mass moving with some velocity v. Notice, because there's a right-hand rule, you can see the direction of the angular momentum is perpendicular to the plane that R and P lie in, which is how cross products work. Here is an example where we are asked to find the angular momentum of different particles. What we have to do is for each particle, we have to write the radius vector from the origin. And so we'll look at that example. So first I'm going to start with mass 1. And first I'm going to start off to say, well, M1 is 2 kilograms. V1 is equal to 4J meters per second. And now when I have to figure out the R1 vector myself, I notice that it goes over in the negative x direction 2 units, so it's minus 2I. And then it goes up 1 unit, so it's plus J. Okay, so when I do the angular momentum for mass 1, it's R1 cross M1 V1. I'm just going to do the matrix method. Notice I pay attention to the direction. And this is going to be 0, 8, 0. So what I did is I multiplied the mass of 2 times the velocity of v to do the mv, and that's where I got the 8, but it was in the j direction. And if I look at my 3 matrices that I have, oops, this one was wrong. This was 1, and this should have been 8. I actually did the J1 first. So it shouldn't come as a surprise that this angular momentum does not have an x or a y component because of the fact that the 2 vectors I'm working with lie in the xy plane. That's how it works. So the angular momentum is minus 16. That's kilograms meters per second, meters squared per second, and it's in the k direction. I'm going to do mass 2 over here. It's really the same process, just doing it for different values. R2 this time looks like this. It has an x component of 4 and a y component of 1. So and 4 times 5 is 20, so I'll just write that 20 in the x direction. If I use the lesson I learned from the first one, I know that there's not going to be an x and y component for this angular momentum, so I'm just going to do the k matrix. So I get minus 20 kilograms meters squared per second in the k direction, or the z direction. It's minus. All right, and we can do the third one on the next page. Here's my R3. R vector has a positive x of 2 and a negative y of 2. So L3 I'm going to take the mass times the velocity for the momentum line, and that's in the x, it's in the x direction, so it's just 3. Again, I already know there's no x and y component because that's how cross products work. The two vectors I'm taking the cross product of are in the x and y direction. Oh, what did I do here? So k is 2 minus 2, 3, and 0. So I get 0 minus a minus 6. So it's 6 kilograms meters squared per second in the k direction. So kind of going along with what we learned previously and the fact that we see that everything has this rotational equivalent. Remember that we saw, because we can write Newton's second law is F equals ma. A is the derivative of velocity with respect to time. But when we introduced the concept of momentum, and if we said if mass was constant, we could write the force as the derivative of momentum with respect to time. So we might make the assumption that if we substitute all these quantities by their rotational equivalents, that we would come up with the fact that torque would be equal to the derivative of angular momentum with respect to time. So we think this is true. So let's look. So let's try to show it. So we're going to start off with the fact that force can be written as the derivative of momentum with respect to time. And what we're going to do is to try to change it into our rotational equivalent. We know we want torque on the left-hand side, so we're going to take R cross this entire expression. And so this is indeed torque, but what we want to say is this, the derivative of angular momentum with respect to time. So we have to figure out, is that true? So let's try to figure out what that is. L is R cross P, so let's take its time derivative. So we have to use the product rule on the right-hand side where we take the derivative of R with respect to time, cross it with P, and now we're going to take R cross the derivative of P with respect to time. And we notice that we have this value. If this is 0, then we could say dl dt could be written as R cross dB/dt, which is what we're hoping, because then we were right about torque being the derivative of angular momentum with respect to time. So dr dt cross p could also be written as v, because dr dt is v, cross mv. This is equal to 0 because v and mv are parallel. And the cross product of parallel vectors is actually 0 because they're in the same direction. There's no angle between them. So our answer to the question, if this was dl dt, the answer is yes. So what we have found that indeed torque. No. Oh, okay. That's your friend.
Sorry, I got trouble.
What?
I mean, like, that she told students, like, oh, don't look at the dog at the eye. It's
Sorry about that noise. I have the cheap version of this software, so I can't go back and edit it. So let's just keep going. Okay, so what we came up with was there is indeed a relationship between the sum of torques and the derivative of the angular momentum with respect to time. So that basically it's saying that if a system has angular momentum, the way that it would be changed is through the application of some net torque. And so as we go through that, like previously we defined angular momentum as R cross mv or R cross p, however you want to look at it. Here we're kind of assuming that this is a point mass. But if you have more like a rigid body, you might want to think of it in a different way. And so then we can sort of go back and do our exercise where we try to sort of imagine what would this expression look like if I substituted linear quantities with angular quantities. And if you do that, and we have angular momentum, we would replace mass by the moment of inertia, and we would replace velocity by angular velocity. And it is actually true, this relationship does hold true, that for a rigid body rotating about some axis, we would define its angular momentum as a product of its moment of inertia and its angular velocity. Notice in that expression, I don't know why the arrow was here. Must be a problem with the slide. The angular momentum gets its direction from the angular velocity vector. So we use the right-hand rule where we curl our fingers in the direction of the rotation, and our thumb will give us both the direction of angular velocity and angular momentum. So, just like we had conservation of momentum, we have conservation of angular momentum. So just reminding you that we said net torque gives you some time rate change of angular momentum. If the net torque is equal to 0, then this time derivative is 0, which follows that the angular momentum must be a constant, because if we take its derivative and we get 0, that means it's a constant value. This idea has a lot of applications that we might not be familiar with, but once we see them, it'll make sense. So a common demo is to have somebody stand on a turntable with some weights extended and give them a slow rotation. So the idea is that they have some initial moment of inertia, which is equal to that of the person, plus the 2 masses times their distance squared. So this is the contribution from each of the dumbbells, here and here. And so when they have them outstretched, their arms outstretched, the radius of the dumbbell masses is relatively large, which gives an overall higher moment of inertia. When the person pulls in their arms and as a result pulls the dumbbells into a much shorter distance from their axis, the moment of inertia decreases, which means then their turn rate will increase, because the idea is your initial moment of inertia times your initial angular velocity is equal to your final moment of inertia times your final angular velocity. And so in this case, I final was less than I initial, so that, because the product of these two has to be constant, that means that omega final has to be bigger than omega initial. So let's do an example of a problem like this. So we're doing I initial, omega initial equals I final, omega final. The initial moment of inertia is that of the professor and the stool, which is 3 kilograms meters per second, but then you have the two weights held at a particular distance from axis of rotation, and so that's omega. And then, so this is the total moment of inertia of the professor and the masses. That's how we're writing it. The masses are just, each mass has a moment of inertia of just mr squared, because they are like treated like point masses. And then what happens is the moment of inertia when he pulls the masses in is only changed because the radius is different. So let's put some numbers in. He's initially holds them at 0.75 meters squared. His initial rotation rate is 10 revolutions per minute. He pulls them into a distance of 0.25 meters, so and we were looking for omega final. Now here you might notice I didn't address the units of omega. The reason is that when I rearrange this, omega final will look like the first moment of inertia divided by the final moment of inertia times the initial angular velocity. So this is just going to end up to be a number without units, because it's the same thing. The moment of inertia divided by the moment of inertia, it won't have any units. So I don't have to worry so much about what kind of units omega is in, because it will retain its units, and whatever we get will be in revolutions per minute. If you aren't so sure about that, you can just do the conversion into radians per second, find the final omega in radians per second. You could convert it to revolutions per minute and see that you'll get the same answer as I get here. All right, so I put in the values, did a little bit of calculation here, and omega final is going to end up to be 16.1 revolutions per minute. It's sped up just as you expected. If you look at this picture, you might notice it might remind you somehow of an ice skater, other than the fact that ice skaters don't stand on turntables, but they do spin. And instead of holding weights in their hands, they are just pulling in their arms when they want to rotate more quickly. This still does decrease their overall moment of inertia because of the mass associated with their arms. And so by pulling them in, they do decrease their resistance to rotation. And so they are able to speed their rotation rate without being pushed. All right, so let's look at some examples. Okay, so You have a long thin rod, so it's like here. It's rotating about an axis. There's a small mass here and here. So these are like masses on the rods. And it's asking what's going to happen if these both move out to the edge. This is actually the opposite of the situation with the professor on the turntable. Instead of pulling the masses in, we're kind of pushing them out. So it's going to increase the moment of inertia of the rod and the masses. And so by increasing the moment of inertia, it's going to decrease the rotation rate. The interesting thing in this question is many people want to say, so if I'm going to look at the top view now of the rod, it's rotating about the center, so it's rotating like this. The masses are at the ends. And then what happens if they fly off? So this one will fly this way, this will fly this way. So if they end up going like this, a lot of times the instinct is, well, because we've lost the mass, the rod will increase because it'll have less inertia. But the problem is that the mass and the rods represent a system. And so the little masses, they retain their contribution to the angular momentum. And so as they move along, even though now we'll talk about sort of their angular momentum as being mv times r instead of mr squared omega, notice this is still mrv. So we wrote their angular momentum differently when it was on the rod because we talked about the rotation rate. But when they fly off tangentially, we more focus on their linear motion to write their angular momentum, but it's exactly the same. And so the rotation rate of the rod is not going to change. Okay, so this is a really important question here where we know that this skater has some initial moment of inertia and initial rotation rate. He's going to change his moment of inertia. His moment of inertia final is less than it was initial, so the rotation rate is going to be bigger. That's all through conservation of angular momentum. But what's going to happen to the kinetic energy? That's a really good question because we might just assume that it will stay the same because of angular momentum staying the same, but problem is here that we need to, in order to compare the initial and final angular momentum, we want to write them in the same terms. So from here, we can say omega final is equal to I initial over I final times omega initial. And we're going to substitute this in here. I'm going to work over here so I have more room. So this is how I ended up writing K final. So K final could be expressed as the ratio between the initial moment of inertia squared over the final moment of inertia times the initial angular velocity, sorry. So basically what we're trying to figure out is this quantity, how this compares to this. The initial compares to the final. And because of the fact that, well, the I final is smaller, the I final is smaller, but I have I initial squared, this whole thing is going to be bigger. So K final is greater than K initial. So that's actually really interesting. The kinetic energy goes up as he starts spinning faster. So even though the angular momentum is conserved, kinetic energy isn't. And you might ask yourself, if we go back to the work energy theorem, what was the work that was done? The work was actually pulling his arms in. If anyone is an ice skater, you might know that as you try to pull your arms in when you're spinning, it actually is hard. You have to do work to make it happen, and that represents the work that goes into the system that increases the kinetic energy. It's kind of an interesting result. Okay, so finally, we're going to look at an example where a bullet is going to hit the edge of a disc, and then the disc will start rotating. And again, we're going to look at conservation of angular momentum. Now, the initial angular momentum is just due to that of the bullet. So it's the mass of the bullet times the velocity of the bullet times the radius, because it's just MVR is, from angular momentum is R cross P. And so the magnitude of that is just R and V, because the R and the V are perpendicular to each other. After this, it looks a little different. It's the moment of inertia of the disc plus the moment of inertia of the bullet times omega final. So we end up expressing it two different ways because it's just convenient different ways for the two cases. So we're going to just rearrange this. Okay. And we finally get our angular velocity is 1.25 radians per second. All right, so that is that.